So next, let's learn about combinations. And the good thing is that these are almost exactly like subsets. Like even the math definition, I think, of combinations and subsets is pretty much identical. I mean, maybe there's a technicality in like computer science between them, but more or less they are the same. So even solving these types of problems with code is going to be similar to subsets. For this example though, suppose we're only given two integers as parameters. One is n. In this case, let's say n is equal to 5, and let's say k is equal to 2. In this case, n represents the numbers that we can choose from. So in this case, the numbers that we can choose from are between 1 and n. So in this case, we can choose between any numbers between 1 and 5. And we want to create all possible combinations from these set of numbers. But the catch is that the combinations can only be of size 2. So before, we were doing every single possible combination. Like one combination would be just the value 1, another combination would be the value 2, but these are of size 1 each, so they would not be counted as a part of our result. Before, even an empty set was a part of the result for subsets, but in this case, that won't be the case. We want every subset of size k, and I don't think I mentioned it here, but let's assume that we want the subsets to be distinct. So, 1, 2, 2, 1, these do not count. These are permutations because the order is changing, but we care about combinations where the order is irrelevant. So these are not different. We only want to add just one of these to our set. So first I'm going to show you the trivial way to solve this problem that's going to be pretty much identical to subsets. And then we're going to look at a way that we can actually optimize it at least a little bit. So the idea is going to be pretty similar to what we did before. For every number, we're going to iterate through 1 through 5. So for every number 1 through 5, we have a choice. Do we include it or not? So for 1, we include it or we have an empty list. Same decision here. We can either include 2 or not include 2. And same decision over here. We can include 2 or not include 2. And we just keep going like this. But you notice something. By the time we get here, we already have 2 values as a part of this combination. So why would we add more? Why would we try building 1, 2, 3? It doesn't make any sense. So this is already our base case. By the time that we have a combination of size 2 like this, we are good. Like we're not going to go any farther. So, this is a base case. We stop here. But for the rest of these, we will still potentially continue. So for here, we're choosing between 3. So we could include 3. We'd have 1, 3, or we skip 3 and we are left with a 1. And this is another base case. So we would take this and add it to our result. And because the way we branch this, these are going to be all combinations with a 1. These are going to be all combinations without a 1. And we kind of do that recursively. So every time we branch, we're going to have separate, distinct subsets on each side. So this is pretty much identical to the subset solution, and the code is going to be similar as well. But there's one thing about this, the time complexity. We're branching twice every time, but what power is this 2 going to be raised to? Is it going to be 2 to the power of k? Because each subset is only going to be of size 2. So does that mean the height of this tree is going to be k, where k is equal to 2 in our case? Nope, actually, because that's the problem with this actually. Here we are choosing 1 and here we're choosing nothing, because in so many spots, here, 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 in so many spots, we're choosing nothing. So we're skipping a value. That's going to make the height of this tree actually n, where n is the range of values that we can include. You can see even to make this combination, it was actually at a height of 2. But this combination over here is at a height of 3. And many of the other combinations are going to be at other heights. And the max height is going to be 5. So we can't say that this is the time complexity. We have to say 2 to the power of n is the time complexity. But actually, even this isn't the time complexity. This is just the size of the tree itself. So that's the size of the tree, and for each combination itself, to actually build that combination, the time complexity is a k, because that's the size of each combination. So this is an approximation. This is at least an upper bound of the time complexity. I'm going to show you how we can solve this problem with an even tighter big O time complexity. It's slightly more efficient, though practically speaking, I think this would probably be good enough in most interviews. So let me show you the code for this. So we have our combinations function. We're given those two parameters, n and k. We have our result combinations we're trying to return, and we have our helper function, pretty similar. We're starting at the value 1. So 1 is what we're passing in here. I, in this case, is not actually an index or anything. I is, the actual individual value. We know our range of values is 1 through 5. We just happen to start at 1, so that's what I'm passing in here. And our initial current combination, that's going to be the array that stores what our combination is so far. As we recursively call our helper, comms is going to be the actual result, and that's where we're going to put each individual combination that we're eventually going to return. N is going to be, 5 in this example. K is going to be 2. That's the size of the combinations that we're going for. So we have some base cases here. One is that we have a combination. The length of our combination is exactly equal to k, in which case we're going to take that combination, create a copy of it, and then append it to the result and then return. We don't need to do anything else. But there's actually a case where, the path where we just keep choosing nothing. Like here we have an empty array. We keep just having an empty array. We keep skipping the value, and we will eventually go out of bounds. We'll go out of bounds in the sense that our I value, which is going to be 1 through 5, is going to be too large. Like eventually it'll be 5, and then eventually we're going to choose nothing again, and then our I value is going to be 6. It's going to be out of bounds. We can't include 6 as a part of any of the combinations. It's not a part of our valid range. So in that case, when we go out of bounds, we're simply going to return because we went out of bounds, but we still don't have a combination that's equal to k. Okay, then we can't really do anything at this point, so we stop. But if we don't have any base cases, we have our two decisions that we're familiar with by now. We can either include I or we do not include I. If we include I, we add it to our current combination. We recursively call our helper, where I is, a part of our current combination. And then after that's done, we're going to pop I from our current combination and then recursively call the exact same function with the exact same parameters. But the difference is that I is not a part of our current combination. So this is pretty familiar, I think, if you already learned about subsets. But now let's take a look at how we can optimize this. And it has to do with math, actually. If we have a set of, n numbers, in this case where n is 5, and we're trying to create all possible combinations of size 2, how many possible combinations even are there? Because that's the theoretical limit that we can reach. Because we know we have to create some number of combinations. Let's say that number is x. And for each of those combinations, they're going to be of size k. So this is theoretically the best time complexity we could possibly get. So how can we achieve this? When it came to subsets, we know that the number of subsets had to be 2 to the power of n. We can't do better than that. That's how many subsets exist. But for combinations, there's clearly going to be less combinations than there are subsets because these combinations that we're talking about are of size 2, whereas the subsets were of any size. They included size 2, but they also included all the other possible sizes. So we know the number of combinations is going to be less than 2 to the power of n. Well, the math behind it is it's actually a math formula in statistics. It's sometimes denoted like this. You're getting the combinations where we have n values, choose k of them. It's called n choose k sometimes. It can be referred to as other things as well. But the idea is that this is a math formula, and the math formula where we have n values and we want to choose k, how many possible combinations can we create? Well, this is the math formula, n factorial divided by k factorial multiplied by n minus k factorial. Now, you definitely don't need to know this to solve this problem more efficiently. I'm just quickly going over this math background, but this is more efficient than 2 to the power of n. But let me show you how we can solve this problem by basically creating every single combination that we need without going down paths where we choose nothing and then end up creating a larger decision tree than we actually need to, because it's not super crazy. So another way to think about the backtracking, instead of thinking about it in terms of choices where we can either choose like a 1 or not choose a 1, let's instead think about it like we have, in this case, k spots that we're trying to fill. So in this case, 2 spots. And for the first spot, we have 5 choices. We can choose any number between 1 and 5. So we would have 5 branches for every number between 1 and 5. So next we want to fill the second position. So would we have 4 choices in that case? That would mean for 1, we have every choice except for 1. So we have 2, 3, 4, 5. And then maybe for 2, we also have 4 choices. So 1, 3, 4, 5. And this would be all 2 digits because these two occur at a height of 2. What we're doing here is we're never choosing nothing. We know here we chose 1. So next we have to fill the second digit. We have every choice left remaining except for 1. When we chose 2, we have every choice left remaining except for 2. Doing it this way, we are not ever choosing nothing, so the size of our decision tree has pretty much been minimized. But the problem here is we actually have duplicates. Here we have 1, 2, and here we have 2, 1. So even though they occur in a different order, we don't want to have duplicates occur. So if we choose all 5 values here, 1, 2, 3, 4, 5, and here we can choose every other 4 value, this will result in duplicates like this. So actually we're getting the incorrect result, but we're also making our decision tree larger than it needs to be. Well, to prevent this, what we can do is when we go down the path of 1, we're getting all possible combinations where we have at least a single 1 value in our list of combinations. These are going to be all combinations that have at least a single 1. So the rest of these paths have to generate all combinations that don't create a single 1. So that's what we have to do with the rest of these. So when we have our 2 over here, this can never include any more 1s. So the only choice this guy has is to include a 3, a 4, or a 5, because we said that this path will have at least a single 1, but we actually know it's going to have exactly a single 1, because with these combinations, we can never reuse the same value because we do want distinct combinations. So this is the path with exactly a single 1. These are paths without any 1s. And in fact, this path is going to be the path with exactly a single 2. Because remember, we don't want this path to have any duplicates with any of the other 3 paths over here either. So that's how we're going to handle this. This is the path that contains a single 2 and never includes any 1s. So this path is going to be the path that includes a single 3, but never any 1s and never any 2s. So this would have 2 children, 4 and 5. Obviously, this is getting messy. Sorry about that. And then this 4 would follow the similar pattern. This 4 will have a single 4, but never any 1, 2s, or 3s. So the children of that 4 would just be 5, and then the 5 would actually not have any possible children. So at this point, we would not go any lower here because this needs to be, remember, have 2 digits in it for us to add this combination, but we can't really choose anything from here. So we wouldn't really continue down this path. And at this point, we actually have all of the possible combinations that we would include. Notice here that we do not have any possible duplicates, but these are all possible distinct combinations we could create. Let's follow our formula. First, let's count how many we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see our formula. Remember, our formula is n factorial divided by k factorial times n minus k factorial. So this is the formula. Let's plug our values in. N here is 5 factorial divided by k factorial, which is 2 factorial, and then 5 minus 2 factorial. So that's going to be 5 times 4 divided by 2 factorial, which is just 2. So that's going to end up being 20 divided by 2, which is going to end up being 10. I mostly did the math in my head, but you can write it out if you'd like. The answer you will get is 10. So that's exactly what we were looking for. We have 10 combinations. So that's the result. So coding this up isn't going to be too different from the regular solution. The only difference is we're going to have a loop here because, as you can see, for 1, we're basically going to every number after 1. For 2, we're basically going through every number after 2 for its children. For 3, we're doing the same thing. And for 4, we're doing the same thing. And for 5, it didn't have any numbers after it. It was the last number in our set from 1 through n. So, of course, it didn't have any children. So this is the combinations code with the pretty much most optimal solution. It has the tightest big O bound time complexity. That said, I don't know if most interviewers or companies will care about you finding like this most precise optimization. I think the solution k times 2 to the power of n solution would probably be good enough. It's a subtle enough improvement that I think in most cases, this optimized version will probably not matter. but this type of pattern can definitely come up in other backtracking problems. In many problems, this is the only way to do it. It's kind of the same pattern we saw before where we were creating subsets, but we were not given a distinct set of input numbers, because here you can see we have a loop. But so our combinations is set up the same. Our result is going to be a list of combinations. We're starting at number 1. Our current combination is initially empty. We're passing in the result that we're trying to build, and we're passing in n and k. The base case in this case is that if our current combination is of length k, of length 2 in this case, then we're going to create a copy of the current combination and add it to the result and return. Otherwise, if we go out of bounds, similarly, we will return. But for the recursion, we don't just have 2 choices in this case. We actually have a range of choices. If we're at the value I, basically we want to go through every path. I plus 1, right, will be the children for I. So if, for example, we had 3, the children would start at 4 to 5, etc., keep going until we reach the edge of our range. So for that I value, we would pass in basically, j, but adding 1 to it to make sure that we never repeat the same value, right? Like we don't want to reuse the same value. We're not allowed to do that, but also that we never result in any duplicates as well. And then after adding it, we're going to backtrack. This is part of backtracking, right? Where you make a decision. We have 3, we add 4 to it, and then we, handle the recursion, whatever, maybe this would have some children, but then we pop back up. We undo this, we backtrack, we pop the 4, and then we try going down another path where we have maybe 3, 5. That's the idea behind backtracking. That's why we're popping here and then trying a different possible child. Other than that, the code you can see is pretty short. It is the same as the other backtracking solutions we've looked at so far, just that this has a slightly better time complexity. That's what I was trying to kind of illustrate with this example. Another variation of solving this problem that's slightly more efficient. And maybe this would have been the natural solution that you possibly came up with. Maybe you didn't think about it in terms of just 2 decisions. You were already thinking about this kind of approach.